What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencastr. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencastr is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencastr's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMath, and you'll get 30% off your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
The world around us is a four-dimensional world. There are 3 spatial dimensions and 1 temporal dimension. Many of these objects emit an almost unfathomable number of photons. As we developed as creatures on this planet, we gathered the ability to sense the world around us. And given the amount of information represented as photons, it is no surprise that we developed an organ for sensing photons. But because of the amount of photons that are involved and our relatively limited computational resources, it is necessary to develop shortcuts if you want to simulate a 3D environment in silico. So what is ray tracing? How is that different than what happens in games? And what does Ptolemy have to do with 3D graphics? All of this and more on this episode of Breaking Math. Episode 74, Lights, Camera, Action. I'm Sophia.
And I'm Gabriel.
And this is Breaking Math. We're going to do an episode on 3D graphics. So why this episode, Gabriel?
Because recently I landed a dream job of creating 3D graphics. It's still an engineering job, but I create models of trucks and planes and vehicles, and I also create them in a destroyed state as though they've been in an accident. And I'm learning all about 3D modeling and video game graphics and simulations, and it's so exciting.
And it does sound pretty exciting because I know that merging art and engineering is definitely one of your things. What cool things have you learned recently? Because you've been doing this for what, a couple months?
Sure, yeah. So actually, for our listeners' sake, what's interesting about this episode is I have been in computer graphics now. I landed this job last November, actually. And just so you know what software I use, there's some fairly well-known software that I use, like Autodesk Maya, as well as Adobe Substance Painter and all of the other Adobe products like Photoshop and Illustrator. But I also heavily use a free software that you can literally download right now on just about any computer called Blender. Blender is actually, at this present time, my favorite. So I've done a lot of practical applications of 3D modeling. It's amazed me how it works. Like, if something's supposed to be, say, a round cylinder, I can make like a 6-polygon hexagon, but then I'll just right-click it and I'll say shade smooth, and suddenly the computer knows to make the light bounce off of it, although as though it's perfectly smooth, even though it's still a six-sided hexagon, if that makes any sense.
Oh yeah, totally. Yeah, it's one of the tricks you learn early on. I think in at least it used to be in Lightwave. Lightwave is this old dinosaur computer program that nobody uses anymore.
Yeah.
I've technically done 3D graphics longer than Gabriel. However, it's been so long since I've done it that a lot of my knowledge is outdated. However, a lot of the math is something that I learned at the university.
Yeah, there's math underlying all of this, and this is the exciting part. Now, I want to just geek out about computer graphics real quick. I think I first got introduced to computer graphics when I was probably in second grade, around the time Terminator 2 came out, and they just began to use computers heavily in graphics in movies. And I think that's a James Cameron movie, the same guy that did Avatar and Titanic. He did Terminator 2. He did one movie before that with some heavy computer graphics. I think it was called The Abyss. Did you ever see The Abyss?
No, I did not.
Okay, check it out. So in The Abyss, it's a movie kind of like E.T. or Close Encounters of the Third Kind, where there's an alien species and it's far underwater. And this alien species has like a telekinetic ability where it can move water in any shape. And I've always been very curious. There's this scene in The Abyss where this water like lifts out of a container and like moves around like a tentacle. That's all done using CGI. And I always wondered if the ability to do that in computers came before the idea for the movie. And then I think James Cameron did that, and he thought, wait a minute, I could do some really cool stuff in Terminator with this. He then made the T-1000 Terminator, which is pure liquid metal and is able to turn into any shape. All done with computers, of course.
Oh yeah, and there was a lot of, from what I recall, a lot of advancements made during the movie, actually, on computer graphics. Specifically, I know that the way that they handled reflection with kind of like background maps had been done, but getting it to work in a composited environment was the challenge.
Yeah.
So we're going to talk about all that kind of stuff, but I guess we're going to also talk about we're going to answer one question, which is what is the best CGI that we've seen?
Yeah. Oh, for sure. Absolutely. And actually, I'll go and answer that now, if that's all right. I already said this before, but in the movie Terminator, back in my single days, that was one of my go-to conversations on dates, because I was always blown away by so many scenes in Terminator 2. For our listeners who haven't seen it yet, I highly suggest just go to YouTube and type in best scenes from Terminator 2, or just watch the entire movie. In this movie, you've got this villain that can turn into liquid metal. There's a part where he is in the floor, like a tile floor. He melts himself down into a tile floor. Then at the right time, he just rises out of the floor. And all of that was done with early CGI, but it was done so spectacularly well that it was just mind-blowing. There's also a scene where he jumps onto the outside of a helicopter that's still in the air, and he breaks the glass on the helicopter with his helmet. He then like melts himself and as a blob like melts into the helicopter and then reassembles himself. And that is some of the most spectacular CGI, even to this day. And we're 30 some years later. It was done so well. Check out Terminator 2 and pay careful attention to the graphics and how they do it. So for me, that movie was the most impactful. How about yourself, Sophia?
I think I'll just choose a recent one. Pixar made a movie called Soul, which on the surface doesn't seem like that much of a graphical achievement until you kind of really start watching it. And the kind of merging of 2D and 3D graphics that they needed for that movie, plus some of the obviously new shaders. There's a lot to think about with that.
What a fun episode, because I feel like this episode can fit both with Breaking Math as well as Nerd Forensics, where we're talking about both the mathematics that underlie something as well as the art and the emotional effect it has on us. So I just think that's really cool. That's really exciting.
So maybe we'll have Millie from Nerd Forensics, another podcast, although more explicit than this one. We'll have her on to talk about maybe some moments parts in 3D movies and talk about the algorithms used to achieve them and stuff. But for this episode, we're just going to kind of give an overview of the mathematics behind both like movie CGI and video game CGI, which actually use different algorithms and approaches.
Yeah, absolutely. Yeah, and I've got so much to say, especially what I've learned. Again, I'm only maybe, 5 or 6 months into this, and I'm learning stuff every single day about how this works. So, and also for our listeners, anyone who wants to try this, I said earlier in this podcast, you can download Blender for free, and there are countless tutorials on YouTube that you can do right now.
Nice. Oh, and before we go on, I'm going to just plug a couple of things. You can email us at breakingmathpodcast@gmail.com. You can follow us on Twitter at breakingmathpod. You could donate to our Patreon at patreon.com/breakingmathpodcast. And we do have a poster still for sale. If in the past you've bought a poster but then had to cancel your order, I recommend buying now. Again, we got our whole process together. If you had any issues with posters, just email us and we'll see what we can get done for you. Yeah. But yeah, it's a poster on tensors, which are used in the general theory of relativity. And it's just kind of a fun poster about how they work. All right, so before in the intro, we talked about how many photons there are, and just kind of to talk about like how many photons there are. If you have a 60-watt light bulb, right, of white, it's just an average white kind of incandescent bulb. There's 8.21 times 10 to the 18th photons per second leaving that. So if you think about that many photons per second, if you think about them kind of like grazing your eye, it doesn't actually take that many photons for something to be visible. If it's like really, really dark, sometimes only hundreds of photons are entering your eye. If like you're in the middle of like just starlight in the middle of like a dense forest or something.
Yeah.
And so it really shows how few photons compared to outside get into your eye. And it also shows how you can't really compute this, right? You can't just scatter a bunch of light and then have it bounce around a virtual scene with all these photons. Because even if you reduce that amount of photon into like the billions, you're probably going to get a low resolution image, right?
Yep.
And so how did the eye kind of evolve? I think might give us some clues on how to simulate these algorithms. Does that sound good?
Yeah. In fact, I think there's a really good spot to start here before we get into the math of computer graphics, actually talking about how the eye works, and therefore it gives some context to what a computer is trying to do, or what we're trying to do with a computer and making the graphics.
Oh yeah, definitely. So let's talk about light-sensing animals. Euglena is a genus of single-cell flagellate eukaryotes. It's just a single-celled little animal, dude.
Yep.
So it has a light-sensing organ, but it doesn't give any information except for brightness, right?
Yeah.
So it's like, am I in a bright area or am I not? It's basically a 1-pixel animal.
Yeah, and that's actually so its awareness of its surroundings, as you said earlier. Yeah, it's just, is it brighter or is this darker? That's all it's got.
Yeah, and that kind of gives us a clue to some of the first stuff we have to simulate. So if you think about a point light source, meaning kind of like a light bulb, an idealized light bulb in every direction, if we're just simulating 3D graphics for Euglena, all we have to do is calculate the distance from the light, square it, invert that, multiply it by how bright the light is, and get an approximation for how many photons, right, hit this animal.
Yep.
So that gives us a clue that brightness is already part of the equation. So then we're going to take a look at cup eyes, which are used by planarians. Planarians are like these little kind of like teeny tiny little worm creatures. A lot of drug research is done on them.
In fact, the Bald Scientist podcast, we interviewed him on touring rabbit holes. He works with planarians all the time. That's his favorite worm, I believe.
Oh yeah, I would love to have him on this show too.
Yeah, I'm sure he'd love to be on.
So if you think the planarian, the reason why it has cup eyes is because if you put your hand in front of your face right now and you rotate it around, you're going to see that the place where everything is dark kind of changes. And if you take something kind of brightly colored and put it near your hand, you'll see that your hand kind of turns into that color. So that's kind of how cup eyes work. They give you a general sense of direction, but pretty much nothing else. No clarity, nothing like that. Very, very little clarity.
It's got brightness and direction, correct?
Brightness and general direction. Okay. So it's like very low resolution. So what this tells you is that we're going to have to, talk about the direction that the light is coming from, right? Mm-hmm. Of course, now instead of having just a minimum of one cell to sight into the light, now we have a whole patch of cells, right? And that evolves to become a pinhole eye. What happens is it becomes enclosed like a cavity within the animal. An animal that has this kind of eye is called a nautilus. And the way that this works is by simulating a pinhole camera. So think about this. If you have a red object to your left in front of you and a blue object to your right in front of you, the light from the red object is going to the back right part of your eye, right? Mm-hmm. And the light from the blue object is going to the back left part of your eye.
Yes.
And let's say we increase our pupils until they're the size of our entire eye, so we have some freaky open eyes. As we increase this, more light, like at first, only the light from the blue pupil can get to the spot in your eye through basically one path, right?
Yes.
But as you increase that size, the amount of paths increases. Think about it kind of like taking a bundle of spaghetti and kind of like letting it kind of go loose in every direction. So it's kind of like 2 cones on each side.
Okay.
So that's why things get blurry when you have larger pupils, for example. So that's kind of like what you're simulating with a pinhole eye. And then finally we have lenses. First we're just a protective measure, later filled up with fluid, differentiated normal evolution stuff. And what that did is it changed the field of what we could see, right?
Yes.
So for example, if light were going to hit a spot next to our pupil, it might hit the lens instead and then reflect back into our eye, giving us greater range of vision.
Yep.
That and the pinhole eyes tell us that the pinhole eyes tell us that we're going to need to know where an object hits on the screen, and the lenses tell us that it's going to be something that the lenses point towards us simulating the rays of light, right?
Yes.
So without further ado, I think we should go into ray tracing and video game graphics.
Sure. Now, obviously, there's a whole lot with respect to our vision that we didn't even get into, as well as the vision of other animals. Things like rods and cones and differentiating the color palette that we're used to.
Oh, yeah. Actually, you know what? It might be a good idea to talk very briefly about cones.
Sure.
So red, blue, and green cones are used to sense the world around us. But if you think about it, a computer screen, when it's showing yellow, it's showing red and green, because yellow light triggers red and green receptors about the same amount. So if you project red and green light into your eye is going to see it as yellow, which means that if you have one of those LED bulbs and you set it to yellow, if you have a red object in that room and you have a green object in that room, the red object is going to look red and the green object is going to look green. However, if you have a light from like a sodium lamp, a specific type of sodium lamp called, I think it's a sodium lamp called monochromatic light, or if you take like a prism and you isolate the yellow and then use a lens to scatter that around the room, the green object and the red object will now appear yellow. And the reason why is because it's not fake yellow light anymore, it's real yellow light. And this actually does come up during in some more intense computer graphics stuff that we might talk about later.
Rasterized graphics.
Yeah, and I mean, rasterization really is kind of like the last step in video game graphics, but it kind of gives a clue to how it's used.
Yeah. So ray tracing is a term. It's actually an older term in the history of graphics, and it's made a comeback lately. There's a couple of graphics cards one of them is by NVIDIA, and one of them is by
AMD. Yep.
Very good. So the term ray tracing is actually a very old term. However, it's made a comeback recently with some very advanced graphics cards by companies like NVIDIA, their RTX series, as well as AMD, their higher-end series that are capable of modern ray tracing. We're going to talk a little bit about that, but essentially it's getting a computer to simulate what we experience as light and reflection, and therefore it makes video games look way more realistic.
Oh, yeah, for sure. So yeah, speaking of that, we're going to talk about how a wrong theory in physics led to a good formula for ray tracing.
I love this one. We've actually done entire episodes of this podcast on wrong theories in physics, but one of them is making a comeback because it's so used. I mean, I shouldn't say the theory itself is useful for describing the world, but it literally describes how computers simulate the world. So yeah, it's quite interesting.
Yeah, and I wouldn't necessarily call it a comeback. I mean, it's been here for years, since the 2nd century.
When did the term ray tracing first come out? What's your familiarity with that term ray tracing?
My familiarity with it is that in rendered computer graphics, right, like where you're not doing it live when you want more detail and control,
yes.
Ray tracing is what you're going to use, basically. And the reason why is because, as you'll see, computer graphics makes even more broad kind of generalization. So, for example, area lights are something that is relatively easy to do in ray tracing. So think of fluorescent lights under diffuse panel, for example, in offices, for example. That's an area light. So, but rendering an area light in ray tracing is, we'll get into exactly what ray tracing is, and we'll talk about why that is.
Yeah.
And so, like I said, 2nd century, right? Ptolemy was creating a book on optics. And I'm sure Ptolemy noticed that if you put an object, right, so let's say a coin, behind another coin, if they're both in line with your eye, one is going to be behind the other, right?
Yes.
So it makes sense that there would be some kind of mechanism for kind of like every direction. So like the top part of your eye might have a different mechanism than the bottom part of your eye. It's not an illogical theory, right?
Correct. Yeah, I'd give him that. Give him some credit. It's not illogical.
And so what this theory was that the eye has a bunch of these little rays within it that go out from the eye and bounce around the world and then report back to the brain.
That's amazing. Yeah. And I thought that was amazing. What's also amazing is I wonder if there's any relation to seeing light up eyes, to that being embedded in our subconscious or something.
My guess for that actually is that it comes from predatory cats, because the fovea of a cat will reflect in light.
Okay, yeah, because as soon as you see like red eyes light up, the bad guy is gonna get us. I'm talking about any sci-fi movie or cartoon or whatever.
Oh yeah, I mean like Titans, the Titans in that one.
Attack on Titan?
No, not Attack on Titan. The one with Hercules.
Okay.
Sorry, the one with Hercules. It's Hercules though. But yeah. So this was actually refuted by Hassan ibn al-Haytham in a 7-part book of optics called Kitab al-Manazir. And it was like the first refutation. It was during a scientific sort of philosophical revolution in the Islamic world that happened in the I believe this is like 10th or 11th century.
So before it was debunked, people, or rather this guy thought that eyeballs were like little flashlights. They literally sent out rays of light from each eyeball.
Well, not even rays of light, because rays of light implies that the rays of light go into the eye. It was the idea that light exists separately from eye rays, and then that the eye being a sensing organ sends out these things into the world, which report back. Wow. And I mean, if you think about it, it's not the most like ridiculous thing, right? Because I mean, like if you look at like a tree growing over time versus like a blink, it's easy to think, okay, maybe there's these natural phenomena that are extremely quick that have to do with something as nebulous as sensing, right?
Yeah, I guess you're right. All right, again, I shouldn't talk too much smack about what people did or didn't know back in the day, because right now, what do we know or what don't we know that will be made fun of, in future years. So yeah.
Oh yeah, and what's cool about this method of ray tracing though is that it totally works for simulating the real world around us, right?
Yes.
So like, let's say you look at a mirror, right?
Yes.
The rays bounce off of the mirror onto the scene around you, and then it's just like those rays in Newton's optics, where it just talks about like apparent size and all that.
Yes.
If you want to know what I'm talking about, just go look up optics on Wikipedia and look at apparent size. Mm-hmm. But yeah, so the cool thing about this is basically for each pixel you send out, in the simplest incarnation, you send out one ray for each pixel. And so let's talk about how this works. But before we talk about how this works, we're going to have to talk about the intersection of rays and primitives. All right, so Gabriel,
yes.
Walk us through rays and what they are in vectors.
Oh, for sure, absolutely. Okay, so rays. Okay. So a ray is like it is. If you go with a mathematical definition from 6th grade, it is an infinite line that has a starting point. Or you could also think of a ray gun, like pew pew pew. It's something that has a start and it has a direction and no end necessarily.
Yeah, and the start and direction are both represented by triples, right? I mean, one is technically a point and the other is a vector, but they're represented pretty much the same way in the computer, right?
Yes, they are. And
so the rays that we do for a ray tracing thing is, so the way that this is done is you draw kind of like a square in space, kind of like where you're going to look out from. You could think of this as kind of like if you take a pic, if you've ever like taken a picture, but before you kind of put your fingers in L's and put them at opposite corners of a box. It's sort of like that. You set up a bunch of points in a grid. Like,
what's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the "did we just hit a million orders" stage? Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
That.
Yes.
And then you have all the rays start at some point behind here. So behind the square that all go out to the different points on the square. So that's how the rays are defined. Does that make sense?
Yes.
And so we send all these rays out, but how do we know what it intersects with, for example?
So obviously, with respect to, what we see and how our eyes work and what our eyes detect, that's one thing. But then how a computer works, that's a whole another thing, which we'll get to, an exciting point here in a little while.
Oh yeah, and let's just think mathematically, right?
Yes.
So let's talk about some primitives. There's a few types of primitives. A common one though is a sphere, because you could technically render a scene with a perfect sphere in it. So a sphere is so how do you define a sphere, Gabriel?
Oh gosh, a 3D object that of a given length where every point on it is the same distance from the origin.
Yeah, you got a center, right, and you got a radius.
Yes.
And so you could define the points of a sphere as such, all p that are in S, such that p minus c, the length of that is equal to r. So now let's derive a ray sphere intersection, right? So Gabriel, if we know that that array is the ray is a plus bt, right? For some starting point a,
Yes.
and some direction b, and t is greater than 0, right?
Yes.
So those are all the points that the ray sweeps out.
Okay.
So now if we know that a ray intersects with a sphere, right? It means
Yes.
that it's going to be it's going to satisfy the formula for a point on a sphere, right?
Yes.
So what we do is we set p to a plus bt. All right. So from here, what you do is you take the point. So you have this p minus c is equal to r, which means that a plus bt minus c is equal to r, and that's the point. So now we need to solve for t, right?
Yes.
So that's a minus c plus bt is equal to r.
Mm-hmm.
We're putting a minus c in parentheses. You with me so far?
Yes. Oh, yeah, absolutely. Yeah. And then algebraically, just bt equals r minus in parentheses, or rather plus, because you got to subtract it from both sides. Just algebraically isolate t.
All right. So we got magnitude is equal to radius, right?
Yes.
So if we square both sides, we get a minus. So we got the whole a minus c quantity plus bt squared
Yep.
is equal to r squared.
Yes.
Or minus r squared is equal to 0. So now we're going to set d to a minus c. So we got d plus bt, just for ease, so we don't have to keep writing a minus c. So d plus bt squared minus r squared is equal to 0. So all we do is we plug that into Pythagorean formula. So what is our a term there?
Okay. So the a term would be it would be the coefficient of d squared. So.
B squared, actually, in this
Sorry.
case.
Oh.
Because we're solving for t, forgot to mention.
Oh, of course. Okay. Yeah. So the coefficient of
So for the Pythagorean formula, we got your a, b, and c, right?
Yes.
Check it out. It's d squared plus 2dbt plus b squared t squared minus r squared equals to 0. So in the Pythagorean formula, our little a is equal to b squared, right?
Let's see here. Okay.
So that would mean our b would be equal to
2dB. Okay. Right.
2dB, and our c term would be equal to d squared minus r squared.
Yes.
And yeah, so you just plug that into the Pythagorean formula, so you get negative 2dB plus or minus the square root of 4d squared b squared minus 4b squared times quantity d squared minus r squared all over 2b squared. And we're not going to talk about what that is, but basically you get the 2 points that it intersects a sphere, right?
Yes.
And do you know why 2 points?
Because if it's a ray, if it goes all the way through it, it's going to be 2 points.
Yeah, so
it's exactly tangential, which would be technically 1 point, but.
Yeah, so if you're shooting a basketball with like your ray gun that you were talking about earlier,
Yes.
It'll hit it in 2 places.
Correct.
So yeah, so we got that data. How would we? Any idea of how we would get what the normal vector where it hits?
That's a really good question, actually. So the normal vector obviously is going to be the perpendicular point to any point on a sphere. So every point on a sphere, by definition, will have its own normal sticking straight up. So if you're going from the collision, I think that if it was a straight-on collision, you wouldn't detect anything because your collision point is the same as the normal. But if it's any other point.
Oh, you were very close. What you said was true if you're looking at the point that goes directly from the ray to the center of the sphere.
Oh, yeah.
But if you do it on the side, all you got to do is take the point of intersection, subtract the center of the sphere from that, and normalize that, and that's your normal.
Okay. Normal, yeah, just normalize it, and then that's your normal. As in the mathematical normalizing it. Do you think because too many?
Because it's a normal thing to do.
It is pretty normal, you know. I mean, I did it. You did it. I'm sure everyone's done it here.
Everybody's just going to normalize using these normal vectors.
Normalize using normal vectors. Can we tweet that?
Yeah, we could do that. I think actually I did that.
Did you?
I think so. I think that might have been one of the dorky tweets from last month. Yeah, at Breaking Math Pod.
Yes.
But so what can we do with the data? We use a normal for reflection, and we use the point of the intersection and the ray from there we actually use the normal for refraction too. So, Gabriel, what's reflection versus refraction?
Physics 3 from college. My goodness, I blazed through that class. I'm sorry. So it was reflection versus refraction?
Yep.
Okay. So refraction, think about it this way. If you are going through water and you see that a light ray shifts all of a sudden, that is refraction. Now, that's what you see, but that's not the technical definition. And I want to say that it has to do with the angle that it hits.
Yeah, it's not like, I think it's like tangent of theta 1. Oh, here it is. I looked it up. So the incident index, so that's like, for example, for air, it's like very close to 1.001. For like water, it's like what, 1.6?
That brings me back. I believe 1.6 is right on the head. Yep.
Yeah. So if you wanted to see like what how light would change when it goes into a lens, you would take the incident index, which is basically 1 times sine of how it the incident angle, and the incident angle is just the normal. I mean the angle from the normal. And do you recall how to calculate the angle from the normal?
Oh gosh,
I'll give you a hint. Dot product.
Okay, I don't. It's been too long since. Sorry, guys. I'm still podcasting 5 years out of grad school, and it's been a little while.
Yeah, no worries. So basically, the cosine of the angle between the vectors times the length of the vectors is equal to the cosine. Yeah, you can calculate the cosine with it. So if you have two vectors pointing in the same direction, their dot product is going to be the same thing.
That's right.
Which is like a cosine of 0, which is like 1. If they're pointing 90 degrees to one another, their dot product is going to be 0, which means that their cosine is going to be 90 degrees. So you can actually use that to calculate this using Snell's law, which is n1 sine theta 1 equals n2 sine theta 2. And if you notice, light will it'll kind of straighten out with respect to the normal, right?
Yes.
As it goes through. But when it leaves the light, it does the opposite.
Mm-hmm.
And it turns out that doesn't only work for light, but these imaginary light rays for the eye. It works perfectly too. You can simulate a lens perfectly with this.
So going back to that example with Minecraft, when we said that original Minecraft had 2 maps, one of them I think was for the opacity and one of them for color. I don't even think they had a map for displacement, that would cause a light refraction if it went into the water. I don't recall if it had that or not. Oh no,
I honestly doubt they do because so basically for a reason I'll explain real quick. So just to finish up ray tracing, if a light hits an object, you look at how far it is from the closest light. Or actually all the lights in the scene, and kind of like add together the inverse square law, yes. And that's your new light amount.
Yes.
And also I want to talk real quick about blurry reflection. The way that's done is when a light hits an object, you scatter tons of new rays out. So one ray becomes like 1,000 or whatever, but not that, but like hundreds of rays or dozens, right?
Yes.
And that's how you get things like really kind of like smooth mapping, like more photorealistic kind of stuff is the increasing the amount of bounces that something goes around the scene.
Yes, yeah.
And this is contrasted with real-time graphics. Well, in the way that works is that objects are represented by vertices and polygons. And these are kind of objects in you create a scene with these polygons and stuff in it, which we'll talk about how to do in a second. But basically what you do is you map them into the camera's field of view by using a matrix. So you take everything and you squish it down. So you know how like when you're a little kid, you might think that the mountains are kind of small. You do that with math. you make far away things small and close things big, and you just kind of smush everything down together. So suffice it to say, it's harder to do things like refraction with that kind of thing, because then you have to set up new virtual cameras, which is how it's done in modern computers, because virtual cameras don't really cost much to spin up, but it required a lot of like complicated a lot of innovative algorithms to do the same thing with real-time graphics that you do in ray tracing, because ray tracing will always come out a little bit ahead as far as that kind of stuff goes. But yeah, you're talking about Minecraft and how and the differences between real-time and raster graphics.
Yes, exactly. So this is an exciting thing, and again, this is where it'd be helpful to have a YouTube video for a podcast. For our listeners, if you get a chance, just check out ray tracing in Minecraft. In fact, for all you Minecraft players out there who happen to have one of the newer graphics cards that can handle ray tracing, so something like a NVIDIA RTX 2060 or 2070 or a 3060 or above, any of those things, or even the AMD equivalent. If you open up Minecraft and just search for NVIDIA, there are some worlds that are made with ray tracing enabled, and they have not only the 2 maps I mentioned earlier, I think they have a total of, I want to say 6 maps, where the other 6 all tell the light what to do. And when you play the game, it's just spectacular, because as you walk by a metal object, the light bounces off of it and it looks absolutely shiny. You see your real reflections in things. When you walk by water at night, you'll see the light beams from the moon, and it reflects on the water, and as the water moves, so does the reflections. So it's an eerie, I almost want to call it an uncanny valley effect, but it is like, it's almost hypnotic to look at something with such low polygon counts, such blocky graphics, while at the same time having textures that are convincingly hyper realistic. It's really magnificent.
Sounds good. And the reason why modern GPUs can do that, by the way, is because if you think about ray tracing, we could send out each ray at the same time, right?
Yes.
And you'd get the same scene because the scene is essentially static, basically.
Yes.
And so that means that if you have these new graphics cards that both go quickly and have a lot of the way the graphics card works, it has like thousands of little computers inside of it. So if you do all these thousands of calculations at the same time, that's how that works, basically.
Yes, yeah, exactly. And in any of these worlds, basically, as we've said thus far in the podcast, the computer calculates where the source of the light is from. So if you're outdoors, your main source is going to be the sun or the moon if it's nighttime, and then from that it calculates both the strength, the intensity and the direction of the shadows, and also the reflections. So if you've got wood, you're not going to have a reflection, but again, as you walk by any kind of metal material, you can have a reflection. Also, NVIDIA has a website where they literally encourage users to create their own ray traced enabled textures. I was talking to my daughters about making some lightsabers that emit light, and a really cool environment where you see the reflection of your own lightsaber in the environment around you. We just thought that would be the coolest thing in Minecraft.
Oh yeah, for sure. Yeah, definitely. And that's a cool thing as graphics gets more and more kind of like advanced. We're going to be seeing these developments of stuff looking more realistic, and then perhaps later looking less realistic, kind of like you saw with computer graphics from the 80s to the where they become stylistic as well.
Yes.
And so we talked a little bit about how real-time graphics works, but let's kind of break that down a little bit more. So the way that it happens, you have a graphics pipeline. So first you kind of take your objects and you morph them, do whatever you're doing to them. So for example, if you're doing like a game where somebody's walking, you deform what's called the T-pose, which is with arms out to the sides facing forward. And you deform that using a rigged model, which we'll talk about that a little bit more next time. But you deform it and you have this new set of points, right? Let's say we have a camera, right? And we're looking at this object, and this object is moving forward. Mm-hmm. How can we, the way that we represent it moving forward is actually with a matrix. So this character would be walking kind of like the way that they see it is in place.
Yes.
However, their kind of position matrix is moved as they walk, which causes the illusion of walking. And then when you multiply that by the camera plane, you get a projection onto screen coordinates.
Yes.
So you know where all the polygons are. And then finally you do clipping. And what clipping is you take all these triangles and you see if they intersect one another. And if they do, you kind of clip them, you kind of trim them to size, right?
Yes.
And you also clip things really close to the camera and really far away from the camera to minimize what you do.
You know, if you ever want to see a really great illustration of all the concepts that you're talking about, just do a search on really bad CGI or beginner CGI. Since I've been modeling myself, I've joined a number of Facebook groups all about CGI, and people will often, as a joke, put their first ever animated rig, and it is so poorly done, but it's obvious that the steps that the character is taking don't at all line up with their movement through the world. So it's quite interesting.
Oh yeah, for sure. So let's say we have a bunch of objects in a scene, right, in a video game.
Mm-hmm.
How do we know which polygons are in front of? Well, actually, let's just say we're doing a ray tracing scene, right? We're ray tracing a scene with like, let's say a million spheres, and let's say we're doing like, my first ray tracer program. How would you check which sphere a ray intersects with?
Okay, so with again, I'm assuming, and again, I hope I'm understanding you correctly, but all the information in terms of placement of the object and the size of the object would be put in by the original programmer, right?
Oh yeah. We're imagining that we have like a million objects stored in memory.
Okay.
And they're all within the view of the camera. Somewhere in front of others, etc.
Yeah.
How would you tell which object a ray hits first?
Okay, so probably just from the player standpoint, probably the intensity.
Well, actually, I'm just talking about we're talking about a rendered scene here,
Okay.
actually. But we're talking about like you send the ray out.
Yes.
How do we know which object it intersects with? Because it might intersect with more than one, right?
Okay. Yes.
So what would you do if you were a ray tracer?
Okay, so you mean if I was the one who? Okay,
If you were a ray tracing program?
Okay. So based on the instructions given by the programmer who made the scene, there's going to be a database or a matrix that's going to say, exactly like it'll have a numerical value with how far apart things should be, and like that's going to inform how the ray tracing is done. And
that's part of it. But if you think about it too, like when you're writing this program, you're gonna have to check every object, right?
Yes.
Because you're gonna have to check, does it intersect this object? Because the computer doesn't know that off the hand, right?
Yep.
And that can take a long time because you got to check not only which objects it intersects, because you got to test every object for, but which is the closest. So you have to save all the intersections and get the one that's nearest to the camera, right?
Yes.
So the way that this is handled is with something called bounding volume hierarchies sometimes.
Okay. I did not know that. That's a new one.
And it's a really cool algorithm. So what happens is, let's say you have these million objects, right?
Yes.
About half of them are on one side, about half of them are on the other, right?
Yep.
So we could do two boxes and calculate which objects are within this box, which objects are within the other box, and which objects are perhaps within both boxes. And then we divide it again, but in a different axis, and we divide each box so it contains exactly half the objects. And we keep doing that until we have this tree in memory. So now if we wanted to see which object a ray intersects with, we send it out and it hits the bounding volume hierarchy. So yes, we know at least one object is going to be made, right?
So if I'm understanding you correctly, the bounding box hierarchy is a computer's way of just kind of eyeballing it.
Yep, pretty much. It's real. Oh, I get it now. But but it totally is a way of like eyeballing it because that was good. Because it's kind of what you do naturally, right? If somebody told you to find something, you could be like, okay, is it in this side or that side?
Yes.
So you send out this ray now. And now it has to check. Okay, does it fit in the left half million or the right half million? And then there, it's like the front 250,000 or the back 250,000. And then, so basically all you have to do there is check about 20 pairs of objects before seeing what it intersects with this piece of light.
Fascinating. Wow. Okay. Cool. That's exactly computational eyeballing it.
Oh, I know. Yeah. That's what I really like about computer science. It's the science of being lazy. We've discussed the algorithms that are used for the two primary forms of computer graphics. One type for realism and the other for speed. Both of these algorithms rely on simplifying the way that light actually interacts with our eye, both over space and time. This was one of the dreams of Ada Lovelace, one of the first computational mathematicians. On our next episode, we talk about more specific algorithms for computer vision and sometimes that films and video games have driven these advancements. I'm Sophia.
And I'm Gabriel.
And this has been Breaking Math. Email us at breakingmathpodcast@gmail.com. Support us at patreon.com/breakingmathpod. Tweet at us at breakingmathpod. And also, Gabriel, you had a few recommendations for resources if anybody feels gung-ho after this episode, and I have a couple too.
Oh my gosh. Yes, I do. So first of all, I'm working with a lot of my nephews, as well as one of my high school friends' 14-year-old son. Everybody is interested in computer graphics right now, mostly because of me. Blender is free. It's freeware, and it's fantastic. So I would say
it's industry grade.
Yes, it is. And not only that, but there's so many websites that will offer one free course, and then they'll offer a lot of paid courses if you like the free stuff. I did the entire free course available at cgboost.com. I don't mind promoting them because it's free. And I did the course where you make a 3D model of a bunch of apples in a bucket, and I showed that to you last time you were at my house.
Oh yeah, for sure.
Yeah, it was amazing. And you literally you take actual photos of apples and you map them onto a 3D apple that you've created, so it actually looks photorealistic. Then you add a bump map to it so that the apple peel is uneven and bumpy like an actual apple. It's amazing.
That does sound cool.
Yeah. So just I would download if you're looking for a hobby this summer. Just download Blender and go to YouTube and type either sculpting in Blender or make something in Blender. I saw somebody do an Iron Man mask in Blender. It was really, and then 3D print from Blender. You can do that.
Oh yeah, and if you wanna look up some of the ways that people have advanced the state of the art, I would always check out SIGGRAPH papers. There's websites on the high seas where you can find it. You could also email the authors, and they could take their time, but they usually will send you a paper. And a lot of times, if you go to their website too, which there's often these computer graphics people have websites, you'll find sometimes models, sometimes programs, sometimes C code, whatever to kind of interact with this stuff. And there's whole communities of Blender plugins, shaders, models, etc. All right, sounds good. Oh, and also for next time, we will have a Discord set up for Breaking Math fans. So until next time, lights, camera, action, or something. I don't know how to end this episode.
Save big this summer with great deals, all in the Baker's app. Get red, green, or black juicy seedless grapes for $1.88 per pound with a digital coupon. Then buy 2, get 2 free delicious 12 packs of Coca-Cola, Pepsi, or 7-Up, all with your card. Shop these deals at your local Baker's, less than 10 miles away. Or tap the screen now to download the Baker's app to save big today. Baker's, fresh for everyone. Prices and product availability subject to change. Restrictions apply. See site for details.